Hi everyone, welcome back. I'm Alex Cui, and today we're going to be talking about Unit 5, Neural Networks. So let's get into it. Neural networks are basically a really fascinating, exciting topic because they lay the foundation for some of the great progress and practical improvements we've been able to make in machine learning over the past decade. And so the basic neural network looks like this. Essentially, you have an input layer, an output layer, and a couple of hidden layers, one or more. So what do all these terms mean? Um, you can think of the neural network as just logistic regression, but done multiple times. And so when we learn logistic regression, we would have a bunch of inputs, right, which is the red nodes on the left. And we basically process them using the sigmoid function and the weights in order to get an output. So here we're doing the same thing. The nodes, the circles, represent values, and the arrows represent a calculation. So whether it be multiplying by weight or doing a sigmoid function. And so essentially what we're doing is, for let's say every input unit value, we're going to get one logistic regression result, which is a single hidden layer node. So one of the circles in the hidden layer. And essentially, as you can see, we basically do this multiple times in order to get a final output. And so normally in logistic regression, we would take a couple of inputs and go directly to an output. Here, we've done something different. We've added a hidden layer in the middle. And what that allows us to do is build a lot more complex relationships from the data to build the model. And that allows us to make better predictions. And so let's go into more examples. Some of the reasons why neural networks are so exciting is because of what they can do for us. And so, for example, one basic application is digit classification. Let's say you have some low quality pictures of handwritten digits and you wanted to classify them into the actual number that they are. And so we can construct a neural network that has a bunch of input layers. So there's 784 input values, one for each pixel. Then we have 100 values in the middle, that's our hidden layer. And then finally, we have 10 output layers at the end, which is numbers that we could predict from 0 to 9. And so neural networks are able to perform much better on these type of tasks that require you to understand complex, and very not direct relationships in the data. Another very exciting application are things with having to do with computer vision. And so neural networks can do classification for images, tell you what it is. They can draw a box around the picture in the image that they're looking for. They can do this for multiple different types of categories, like cat, dog, duck, within the same picture, and draw boxes over all of them. And finally, we've been able to segment the pictures in the image, which means that we can draw a very clear outline of the images. And so this kind of technology is enabling things like Amazon Go, for example, where Amazon is basically using computer vision to have a completely staffless, grocery store. All they do is just track where the items are going when the customers pick them up, and if they can detect that someone picked it up, they can charge them for it without them having to actually take out their wallet as they leave the store. There are other really exciting applications, and all of these computer vision type applications are usually powered by something called a convolutional neural network. So it's not important for you to know exactly what the convolutional part means right now, but essentially, if you can kind of see what's going on here, let's start with the faces column. At the bottom, we actually have a visualization of the hidden layer, uh, and and for each set of grids, we can consider that to be one hidden layer. So imagine our first hidden layer is at the bottom. Basically, we're given an input of pixels. So you have an image, so maybe that's like 30 by 30, so we have 900 pixels, we feed that in. Essentially, what every hidden node here is doing is picking up a different line segment and detecting whether that was detected or not. And so at the bottom, just a bunch of different line segments in different orientations. The next hidden layer, which is directly connected to the previous hidden layer, is actually able to build those edges into facial features. And so, we have things like eyes, nose, mouths, etc. That it's building from the inputs that it sees from the first hidden layer. And then the final hidden layer is able to build those facial features into full faces and use basically this type of, let's say, mold to try to detect whether there's a face in the image or not. And so that's why you can kind of practically see why neural networks are so useful, is they're able to build up these complex relationships within the data to get to a face level classifier. And on the right, you can see a similar thing has been done for cars. And finally, there's a lot of very exciting work in recurrent neural networks. And so in this instance, we have the red boxes being our input data. And so to explain, we basically are mapping every word, like neon, for example, into a vector of numbers from that are all binary. And so the model can recognize those vectors as those words and basically feed those numbers into the hidden layer, which is in gray, and do several computations and basically recurrently, which means that they do them back to back after. So basically what will happen is, you add in one word into the network, okay, it calculates a bunch of weights, right, or theta. Then you add in another data point, and it will build those weights not only from the new data point, but also from the previous weights. And this is useful because on a high level, it allows us to model relationships in the data over a span of time. And so because we know that when we have a sentence and we're trying to translate the sentence, it's important for us to know the order, it's important for us to know the relationship between the words. And so that's why by having such a model, we can model those temporal relationships. And these kinds of neural networks are commonly used to power translation, among other things. So Google Translate uses a very high-powered version of this to tell you that the French version of neon is amazing is néant est incroyable, something like that. And so overall, I've showed you a lot of exciting applications about neural networks, but generally, the reason why we might want to use them over logistic regression is that they're able to tackle more complex problems, like classifying images or data with more complex relationships than we could easily find with a logistic regression. If we want to do it with logistic regression, we theoretically could. We could just increase the number of polynomial features we talked about last lecture that we have in the logistic regression model. And so on the bottom right, you can kind of see, if we have two data points, x1, two variables in the data, x1 and x2, we can square them, we can multiply them together in order to get new input variables. Sorry. But the problem with this is this would lead to an exploding number, a very high number of polynomial features as we add more features. So, let's say we want to add, let's say we want to have data points with, 5 basic features. If we add polynomial features, let's say we want to square each of them, and then we want to square each of the data points with each other, we would get 25 total feature, on the scale of 25 polynomial features. And you can just imagine if we have 100 features, this would become increasingly untenable. And so that's why we use neural networks, to more easily model these relationships that give us more accurate predictions. So how do we implement a basic neural network. Let's start with an example data set. So the Pima Indians are located in Arizona, USA, have one of the highest rates of type 2 diabetes in the world at around 50% of the population. And so there have been a really incredible data source in order for medical researchers to try to investigate how diabetes comes about. So let's say we wanted to create a neural network to predict whether a Pima Indian has diabetes based on a variety of health factors. So here we have about 8 health factors, things like the number of times they were pregnant. Oh, and yes, by the way, this is all women. Their body mass index, which is kind of a measure of how overweight or underweight they are, and their age. And finally, what we want to predict is at the rightmost column, it's whether or not they have diabetes. And so we have several hundred data points of people who do or don't have diabetes, and we can create a model to predict that. So let's start with defining, as usual, our hypothesis function. So in this example, we're going to be using a single 2-node hidden layer neural network, and I haven't really explained it in detail what that means, but in the next few slides, I think you'll come to understand what exactly that it means exactly. And so let's use the hypothesis function to guess whether someone has diabetes based on their health indicators. And so throughout this model, we're going to be using the sigmoid function in order to map values to 0 to 1, because ultimately we're making a prediction, and so we want to use the logistic function. So as you can see here, we're introducing a new term in our hypothesis function, this A term. And so A represents the activation node of a hidden layer in the neural net. And so if I have A subscript 1, superscript 2, what that means is 1 represents that it's the first hidden node in that layer, and 2 represents layer 2 because we consider the input data to be layer 1 and the output data to be layer 3. So what we're doing here is basically multiplying all of our input data, x0, x1, x2, by a theta that's specific to that hidden node. All right, and so this is theta 1, 0 of 1, right? Let's say, what does that number actually mean? So theta 1, the 1 represents that it belongs to the first hidden node, and the 0 represents that the theta is also correlated to the first training data variable. And then the superscript 1, that just represents the layer. All right, and so as you can see, there's a pretty high number of thetas here, or weights, that we have to keep track of. But in the coming diagram, I'll try to simplify that for you so you kind of get a better intuition of what these equations really mean. And so going back to that first line, so we're multiplying the input data x0 to x2 by a bunch of weights. And then we put that into the g function, which is just a sigmoid function. And that gives us the value of our first activation node. So we repeat that for the second activation node in our hidden layer, but with a different set of weights. And then finally, we have 2 values for our hidden layer. All we have to do now is just repeat the process. And so our third layer has 1 output node, which is whether or not they have diabetes. And so to calculate that, we multiply our 2 activation node values by a different set of weights that belong to the last output node. So we do the same multiplication, we put it through the same sigmoid function, and now we have a value for our final layer output. And this is also equal to our hypothesis function. So that was a lot of talking, and hopefully this diagram will clear things up. So ignoring the equations on the left for right now, what we're basically doing is, as you can see on the diagram on the right, we're taking the input layer, which is just the values of our input data, right? And so we're using those to calculate hidden layer values. And then finally, we use the hidden layer values to calculate an output layer. And so we can simplify all the math that we've done here in the bottom left. And so you can see we can turn these really nasty equations into a set of three relatively simple ones. So the first one is a1 of 2 is equal to the function g with the input of theta 1 of 1 times x. All right, and so put into English, this means the first activation node in our second layer is equal to the sigmoid of the input data multiplied by the weights that belong to that node, which is theta 1 of 1. All right, and so this is a more simple way we can express what's going on in our neural network. And to just give you some more intuition of how this works, we can pretty much create as many hidden layers as we want and as many nodes within each hidden layer as we want. All that would mean is just we would create more thetas that belong to each node to calculate the outputs. And so the example of the model that you have here is not the general neural network. It's a very specific example of a neural network. Great. And so this new hypothesis function essentially allows us to build up a lot of complex relationships within the data. Each activation node will hold a different, essentially a different set of patterns for the input data. So the first, we can make something up like the first activation node holds the relationship between age, body mass index, and times you're pregnant, and how that correlates to diabetes. And then that second layer, activation layer, could be representing something completely different. And so to recap, all the input data is multiplied with weights that are specific to each activation node. And then each activation node is then treated as input data to the next layer of activation nodes. And the final activation node just happens to be the hypothesis function and give us a value from 0 to 1, where 0 is no diabetes and 1 is yes diabetes. And so to give you an example with actual numbers, let's say, in this diagram here, each circle represents a node. And so the value in the middle of the circle is the actual value. And you can see that there's some values at the top left of each circle. That's the value of the node before putting it through the sigmoid function. And so the middle value is the actual value of the node. And so here you can see that each arrow also has a number associated with it. So that represents one weight, for example. And so as you can see, starting from the node in the top left, the first input node, we multiply that value by each of the weights, and those go into inputs and are summed in each of the hidden units. So we do that for both input nodes. Now we have this sum of products in the hidden unit, and then we take the sigmoid of those to get the actual activation value, which for the top hidden unit is 0.69. We repeat the exact same process with the hidden units to get the final output value. And so this is just a numerical example of how the hypothesis function works. So now that we have the hypothesis function down, let's move on and talk about the cost function. So here, our cost function for neural networks is almost the same as in logistic regression. Essentially, we're doing the exact same thing in classification. We're just trying to calculate how off were our predictions. Here, our equation is almost the same as the one in logistic regression, with the exception of one term, which is we added a new k term. And so k simply just represents the number of output nodes. In our example, it's just equal to 1. But let's say if you're trying to do a classifier like the digit classifier, you would have 10 output nodes, which each correspond to the probability that that the image is equal to that number. And so the 0th output node is, how likely is this image representing the digit 0? And the 6th output node is, how likely is this representing the number 6, right? And so to take the final prediction for those hidden units, for those output nodes, sorry, you just find the probability that's the highest. And so, as I said, we're changing basically two things. We added a summation from 1 to k, where k represents the number of output nodes we have. And so as you can see, all we're doing is basically summing over the cost in k as well. So which means that we get the cost from each of the output nodes and just add them together. We also changed the theta symbol to something pretty similar looking. This is like a capital theta in the Greek alphabet, and this is just to represent that our theta now is a matrix, not a vector. So it's a two-dimensional kind of array because we have so many. Basically, we have so many weights now for the neural network. In our example, k is equal to 1 because we only want to classify if they have diabetes or not. So the expression basically becomes the same as a cost function for logistic regression. And as usual, we want to try to make j theta closer to 0. It just means we're less wrong. Okay, so finally, let's talk about backpropagation. So backpropagation is the term used to describe gradient descent and neural networks, is the simple way to explain it. Essentially, backpropagation does gradient descent on each layer of the neural network based on the cost function so that the cost function can be minimized. And so in this course, it's not really important for you to fully understand how this is implemented, but just for you to know generally, like the general intuitions you need to know in order to do machine learning well. So just when I say backpropagation, just think this is gradient descent for neural networks. We're trying to minimize the cost by changing the weights. And so to give a simple visualization, just to remind you of what's going on, here we basically have a graph of error, right? So blue is less error and red is more error. And what this is a visualization of is, over time, when we train a model, how does this error decrease, right? And so here, let's say start from the very right, where those two lines start. And every arrow is like one step of backpropagation. So basically, we're doing, let's say, a run through of the model data. We calculated, okay, this is how we want to update our weights. We update them, and then we get a new cost function. And we keep doing that until our cost function is very low, which means that we have a good model. The reason why there's two different lines here is just to show you an example of, the blue arrow has a higher learning rate, and so when it's trying to calculate how far it should step, it's going a bit further than the red line, which has a smaller learning rate. And so you can see that the blue line kind of overshoots and then comes back, whereas the red line goes more slowly but steadily towards the minimum error. So now that we have all of the basic components of a neural network down, we're ready to implement a basic neural network. We haven't talked about regularization for neural networks, just because the math is not necessary for you to learn at this point in time. But that's basically it. And so, all this talk about artificial neural networks and the revolution they're doing to AI basically comes down to these simple concepts. So now I want to talk about overfitting and underfitting again, just because this is such an important topic when it comes to neural networks. So just to repeat, when we model our data, we can run into two problems. If a model is too simple, we won't be able to extract enough information from the data to make good predictions. And if our model is too specific and complex, our predictions will not be able to generalize to new predictions. So within neural networks, we now have new ways of both causing and solving underfitting and overfitting. So just to remind you, this is what underfitting and overfitting can look like. Talked about this last lecture, so I'm not going to go too deep into it now. I wanted to introduce new terms for overfitting and underfitting. So bias is essentially a quantity describing how underfitted and generalized a model is. And variance is a quantity describing how overfitted and specific and complex a model is. So often you'll hear people talking about the bias-variance trade-off. That's essentially the same thing as the underfitting-overfitting trade-off we talked about last lecture. So don't let it confuse you. Secondly, I want to introduce this concept of having a training and validation set. So let's say in general, when we're doing machine learning, we get 100 total data points to train off of, right? And we want to produce the best possible model with just that data. Generally, we want to split up our data into at least two categories. We have the training set and the validation set. So essentially, let's say we split the data set into two separate portions. We can use the training set as expected, as what we've been doing all the time. We use it to calculate the hypothesis function for each point. We find the loss function for every point in the training set, and then we do gradient descent on data points in the training set. So we reserve the validation set only for calculating the loss function. And the reason why is because our model never trains on the validation set. Basically, it means that the model has never seen it, it doesn't know about this data, even though it's still valid. And so the validation set loss is a good estimate for how much error the model will have to new data. Because while the model can get better and better at predicting the outputs for the training set, it might not necessarily be getting better at outputting for new data points, as we saw with our previous underfitting and overfitting examples. And so when we're training these neural networks, first and foremost, we want to minimize the validation set loss, not necessarily the training set loss. And I'll show you why. And before I show you why, let's just go into a brief example. So how much do we usually put into the training set and validation set? So let's say we have 100 total data points. Well, often if we have just a smallish or normal sized amount of data, we'll split the training set to have 80% of the data points, so 80 in this case, and the validation set to have the remaining 20%. As data sets grow larger and larger, and now we're dealing with hundreds of millions or more data points, we can shift the split to about 90 training and 10 validation, or even 98 to 2, because essentially, as our data set grows larger, we have less randomness, less variance, and so the data set has a similar enough distribution to the overall data for you to use it as a good predictor of what's going to, what general unseen data is going to handle, is going to look like in the model. So finally, having introduced bias, variance, validation, and training, we can understand this graph, okay? And so this is another way to evaluate under and overfitting. And so on the x-axis, we have, how complex is this model, or how long are we training this model? It's basically a measure of, how much we are under or overfitting it. And then the y-axis is the error, or the loss function. So you can see that there's three scenarios here. If we have a very low model complexity, we're going to have high bias, high underfitting, and the error is going to be quite high for both the validation and the training error. Validation being green, training is in blue. Okay, and so this is generally true of a high bias situation. And so if you notice that, when you're training, you're training like 50 epochs, you notice that your error really isn't going down by much. It's very likely that you have a high bias. So on the right side, we have actually a very different and strange situation, which is our training error keeps getting lower, but our validation error suddenly shoots up and goes up. So what's happening here? Basically, our model is overfitting. It has too much variance. And so what has happened is that while the model has gotten really good at predicting the training error, it's basically memorized the answers for the training data set and is producing a worse and much too specific model to adapt to new data points, which the validation error is. Which is why it's so important that we base the quality of our model on the validation error. And so the middle is, of course, the sweet spot. That's where we want to be, where a validation error is the lowest, but a training error, not necessarily the lowest, but good enough. So to give you an example of how we can underfit and overfit in neural networks, a scenario where we're underfitting, we could be using only one hidden layer in your neural network for specific, really complex tasks. We can have only two hidden units in that layer, which is, so as you can see, our example hypothesis function model is pretty underfit. And let's say we only train on the whole training set about like 3 times, so not giving that much time to training. These will all produce underfitting in various degrees, and depending on how complex your task is, it might be enough, it might be too little. If we're overfitting, we could be using 10 hidden layers for a very simple task in our neural network. We have 100 hidden units per layer, and be training on the full training set 200 times. So this already would take ages to compute, and it would give you a model that's far too specific and picks up on too many specific details that don't generalize well. So what are the solutions? Okay, so the first 3 solutions are stuff we talked about in the last lecture. The fourth solution is, now to counter underfitting, we can stack more hidden layers, or we can add more hidden layers. And we use the word stack because it's kind of like we're connecting one hidden layer to another, finally to an output. And so it's like we're stacking them up. So the reason why this helps with underfitting is it allows the model to build more and more complex relationships within the data. So you can visualize this with the convolutional neural networks examples we had earlier in the slideshow. So if you flip back to the example with the faces and the cars, as I said, each layer represents something completely different, either the shapes, the facial features, or the faces themselves. And so this wouldn't be possible if we didn't have enough layers in order to, well, it would be possible, it would just be much, much harder. So having more layers allows you to pick up on those relationships. Also, we can add more nodes to each hidden layer. This allows us to capture more patterns in the data, because each node understands roughly a different pattern. So for example, an example I used earlier, a node could represent whether recent pregnancy combined with old age results in diabetes, or something like that. And so it's important to have enough, and sometimes adding more nodes can improve your model. So there are also solutions to overfitting. So the first 4 are from the last lecture. 5 and 6 is basically the opposite of what we did to counter underfitting. In general, the basic way to explain these solutions is that by decreasing the complexity of our model, we can prevent it from making observations that are too specific to the training data that don't exist in the new unseen data. And so, as you can see now, we're basically playing a balancing game between bias and variance. And we have a lot of hyperparameters. So things like the learning rate, number of hidden nodes, how long you train for, how many hidden layers you have, etc., etc. And as you go further in machine learning, the number of hyperparameters just increase. And so we want to pick the best hyperparameters so that we get the lowest validation set error. And sometimes we won't know which settings are the best. Machine learning tends to be very variable, and between different machine learning problems, you can have completely different set of hyperparameters. And so what we can do is a basic grid search. And so in grid search, we basically run several for loops that try every combination of hyperparameters. So um, every like number of layers, like within a given range. So let's say 1 to 10, and we also try several different activation, um, learning rates, and that would already give us several dozen scenarios to try. And so after a long while, a lot of training, we can find a combination that produces the lowest validation error. So this is a basic visualization of a simple grid search with two parameters. And so we have one parameter going from 0.01 to like a bajillion at on the y-axis, and we have one that's going from a very small number to 1,000 in the x-axis. And so each square on this graph represents one result, which is the specific gamma with that specific c trained on the model. And so as you can see here, they found that the best validation accuracy was kind of like 0.01 gamma and about 10 c. Oh, it doesn't really matter what these parameters mean. It just goes to show you this is how we can find the best set of parameters by just running the model with a lot of different parameters. So finally, having all this said, how can we actually implement neural networks? Because I didn't give you all the math, and I didn't want to, for how to implement neural networks, you might be thinking to yourself, well, does that mean I can still use it? Well, in fact, because there's been so much development in the open source collaborative coding community, there are now very simple packages you can use in order to train neural networks, in 30 lines of code, literally. And so I'm just going to give you an example and talk through it so that you have a basic understanding of how to do this yourself. And so let's talk about a specific example having to do with the diabetes data set. Just remember, column 1 is and column 2 are like the same code. It's just column 2 happens after column 1. Okay, and so might use a pointer for this. Oops. There we go. And so here we're using a package called Keras, and what this does is it gives us a nice wrapper that allows us to very simply set up neural networks among other types of machine learning models. And so here we're using some of their models and layer types, and we're also importing NumPy. Okay, so let's load the Pima Indians dataset. Now we just split these into the input x and the output y. Alright, and so the first 8 columns are the inputs, and then the last column is the output. So here is where the magic happens. Now we create the model. Okay, and so we set up our model broadly to be a sequential model. And all that means is that each layer is going sequentially from the beginning to the end. And so basically, it's what you would expect from a neural network that I've described to you. All right, so don't worry too hard about like what sequential means or what all other alternatives are. Here, what we're doing is every time we call model add, we're basically adding a new layer to our neural network. And so here we're adding a dense layer, which means that basically everything is connected to everything. So every hidden layer, a hidden node, for example, will be influenced by every node in the previous layer. So that's what dense means. And let's say we want this hidden layer to have size 12, so 12 nodes. The inputs are going to be dimension 8, which corresponds to our x. And then these initialization and activations, you don't have to worry too much. But basically, ReLU is a different type of function. So we're using the sigmoid function previously for logistic regression. ReLU is a little bit similar, not quite, but it's been shown to have better run times and better accuracy. Okay, so now we do this all again. We add another hidden layer. So this one has about 8 hidden units, which is um, a good number. Doesn't really matter too much, and its parameters are the same. And so we have a model with 2 hidden layers, feeding from one to the other. And then finally, we add our output node, which is simply a hidden layer, you can think of it, with only one node, which is whether or not they have diabetes. And here the activation, usually for outputs, we use sigmoid because it gives a nice distribution from 0 to 1. Okay? So this is all the code we need to set up the neural network. And all the heavy lifting has been done for us by the authors of Keras and other packages. So this is really great because it makes machine learning really accessible to people who don't want to write the code from scratch. So next, finally, we just set some final parameters on the model. So we set a loss function, which is binary cross entropy. It's not super important that you know what exactly that is, but we could have also had the mean squared error, which is what we use in our examples in the slides. We have an optimizer. This is what we use for gradient descent. There are actually multiple different algorithms to make gradient descent faster, and so Atom happens to be a particularly good one. And then finally, we use the metric of how do we determine what metric do we want to use to determine how good a model is, and here we use accuracy. Finally, we just fit the model. So we plug in our x, plug in our y, tell the model how much epochs, so how many times do we want to go through the entire training set, which is 150 in this case. We want to specify a batch size. It's not important that you know what this means, but essentially it means how many training examples do we look at before we do one round of gradient descent. And so sometimes you can have a batch size equal to the number of training examples, but it can also be faster if you make these updates with a smaller batch size and just make frequent updates to the weights. And now we've basically done all we need to do to get a great model. So this will take a couple of minutes to run. You can get a model now that you can save. You can use it to predict on new data points, etc. And so what I'm trying to show you with this example is this is how most people will work with building machine learning in, like, let's say a career setting where you don't have a lot of time to implement something from scratch, and you have a lot of these great tools out there to use in order to create your models. And so what's key is knowing how to do those hyperparameter tuning. Like, you can see why I talked about it so much. It's because what are you actually doing when you're writing this piece of code? You're basically specifying a bunch of hyperparameters, right? Because the model itself has already been implemented here. What your job is to find the best settings for this model to get the best results. And so things like Keras make it easy. So having all that said, finally, let's try to do an assignment with digit classification that I've been talking about throughout this presentation. So in the homework assignment, you'll be implementing a neural network to categorize handwritten digit images with the Jupyter file. So I've left most of the implementation in there. So there's not much you have to implement aside from the hypothesis function. But what's important in this assignment is for you to investigate the hyperparameters, so the number of layers, hidden units, training time, etc., and see how that affects your output. And so that will be a big part of the discussion. And if you have any questions, ask the instructor, fill out the discussion forum.
At the end, you will have created a basic machine learning model that can categorize handwritten digit images.
So thank you very much for listening to me give this presentation. I'm Alex Cui, and I hope you had a great time learning and have a good time doing the homework assignment. I'll see you later. Bye now.